All right, welcome everybody to Codecamp. Thank you for joining. My name is Steve Smith. Online, you'll find me as Ardalis because Steve Smith is a crazy common name. This morning, afternoon, wherever you are, I'm going to be talking about clean architecture in ASP.NET Core applications. This is a talk I've given several different times, and sometimes it's a little bit longer, sometimes a little bit shorter. So I've slimmed it down a little bit. I want to make sure that we have a little bit of time at the end to kind of look at some real code, kind of see how all these pieces fit together. But before we get to the real code, I want to kind of lay a groundwork of some principles that kind of describe what we're looking for in architecture, why some things are better than others, and how we can make some decisions about what is or isn't a good architecture for our applications. I do have some other resources that you'll find online if you're interested in learning more about these topics. I have a course on Pluralsight. Probably the best course to watch related to this topic is my Domain-driven Design Fundamentals course with Julie Lerman. So you can check that out. I have a totally free PDF ebook that's actually updated for .NET 5. The slide still says Core 3.1, but it's .NET 5 now that you can find at the link shown here. It's also available with the eShop on Web sample. So if you just Google for eShop on Web, you'll find a link to this book that you can get as a PDF. I do training and consulting for teams all over the world. So if you're interested in probably remote training for the time being, I'm happy to come and help your team level up. And likewise, if you as an individual are interested in improving yourself and fast forwarding your career as a software developer, check out devbetter.com, which is a private group coaching program that I run. You can also get free content from me. I have a newsletter, I have a podcast, I have streaming on Fridays. So you don't have to give me any money. You can just come and get all my knowledge from these sources too. So, all right. So let's start with some principles. There are lots and lots of principles that we can talk about in software development and software architecture. There are a few that I think are the most important when it comes to how we're going to build our systems, how we're going to separate things into different modules and components to make it so that we can maintain them, so that we can share the load between different teams in a larger organization, things like that to help have software that's going to have a long shelf life. So one of the most important principles I think that relates to this is the idea of separation of concerns. And separation of concerns just means that you want to keep your plumbing code out of the main, important parts of your software. So if you look at this refrigerator and you take a closer look, you may find that there's some things in this refrigerator that hopefully you don't store in your refrigerator in your kitchen at home because they don't really belong there, right? We don't really want to keep our toilet brush inside our refrigerator with our steaks that we're going to have for dinner. Likewise, in our software, we don't necessarily want to be mixing how we're doing low-level data access right next to how we're deciding, whether this or that customer is eligible for a promotion that we're going to offer for our website. All right, so there's different places in which those things can go, and we want to avoid mixing those different responsibilities in the same part of the code, whether that's in the same method or in the same class, or even sometimes in the same project. We want to strive for some separation there because these things tend to change for different reasons. So the big three concerns, as it were, that you worry about in terms of the separation of concerns tend to be data access, business rules, and your domain model. If you're following domain-driven design, you'll encapsulate your business logic in what's called a domain model, and then your user interface concerns. Now, there's other concerns as well. There might be cross-cutting concerns. There might be things that you do for security reasons. There might be things that you're doing for logging or auditing or other things as well that you want to keep separate and isolate behind their own interface or in their own project. But definitely as a minimum that your app should be looking at, consider these three that just about every business application is going to have. All right, so then the next principle that we can think about when we're talking about our architecture is single responsibility principle. And the single responsibility principle is all about not doing too much in one class. Now we can take the single responsibility principle and we can use it in tandem with separation of concerns because the two are very closely related. When you're following the single responsibility principle, you're looking for things that might change for different reasons, both being in the same class. And so again, this often relates to these concerns of data access or business logic, but it could be other things as well. It could be specific techniques or operations or strategies that your application is doing within a class, and we can break those up and split them up into different smaller classes that we can plug in as needed for each use case. Okay, so another way to think about single responsibility is that each one of these responsibilities is a reason why the class might change. And so a common misnomer that people have about single responsibility principle is they might have a class like customer manager class, and customer manager only has one responsibility because it's only responsible for customers in the application. But what does it do with customers? Well, it loads them from the database, and it validates them, and it formats them, and it sends them emails, and it does all these things for customers. Okay, well, that's really a lot of different responsibilities because each one of those might change for a different reason. We might decide to store customers in a different way or in a different data store. We might want to format them differently. This time it's XML, tomorrow it's YAML or JSON. How we are going to do those reports could be different. How we're going to send them notifications might be different. And so all of those different components could be split out into different classes that each only has to deal with that one responsibility. There might still be some overarching controller or manager or something in charge of orchestrating, various workflows for a customer, but the low-level details of how each of those concerns is done or each of those responsibilities is managed should be encapsulated in a separate class. Okay, then the next principle that we can use, and single responsibility is actually the S in the solid principle. So if you're familiar with solid, this is the first of those. And then we'll just jump to the end with the D in solid, which is dependency inversion. And the dependency inversion principle is all about taking dependencies and instead of having your code directly tightly coupled to them, just as if you were taking your lights and just hardwiring them into the circuitry and the wiring in your wall, instead, making it so that we can swap out these dependencies, making it so that the dependency depends on the abstraction, depends on the interface, instead of the other way around. And so if you think about how your house electricity works, you don't have, for the most part, your appliances directly wired into the wall. Instead, your appliance depends on an interface. In the United States, that interface looks like these plugs. In Europe, in other countries, those plugs might look different. But each one of the things that you purchase, each lamp, each device, each laptop adapter is designed to fit that interface. And as long as they fit that interface, both in terms of physicality as well as the expected amount of voltage and amps, then they'll be able to plug and play literally with that electricity source. We want our applications to have these same types of features. We want to be able to take an existing implementation and decide that we want to use a different version of that for some reason and swap it out with another one. And as long as it conforms to the same interface, we can make them interchangeable inside our application. So the dependency inversion principle is all about inverting dependencies and making it so that our high-level business logic code doesn't depend on our low-level implementation detail classes, but instead they both depend on abstractions. And when we're talking about .NET, we're talking about C#. Whenever we think about abstractions, we should probably be thinking about interfaces. Interfaces are the most flexible abstractions that we have available inside of .NET. You could also depend on a class or an abstract class, but once you're doing that, you've got single inheritance, so you can only do that once. It's a much more expensive commitment when you're using that type of inheritance. When you're doing when you're implementing an interface, you can implement multiple interfaces. So it's a much more flexible way to achieve this dependency on abstractions. Related to the dependency inversion principle is, of course, dependency injection, which is a very common technique, especially in .NET Core now. It's built in from scratch. Everything uses dependency injection by default out of the box. And dependency injection really works best if your architecture is following the dependency inversion principle. Now, if you've bought into this principle and you kind of get the idea that, okay, I want to have dependencies as abstractions, I want to inject those abstractions into my classes when they're using them, there's a closely related principle called the explicit dependencies principle, and this one's not as well known. So the explicit dependencies principle basically says that your classes should request all of their dependencies through their constructor. And the reason for this is that your constructor is basically the documentation for the needs of your class. It's how you tell other developers and future you what is needed to create and use this class properly. If you have a parameterless generic constructor for a service, that means you're telling everyone that this class doesn't need anything, right? It's a simple in-memory service, right? If you have a calculator service that takes two numbers and returns back their sum, sure, of course, you should be able to just new that up, create var whatever equals new simple calculator, calculator.add 2, 3, you expect to get back 5, right? Now, if you ran that and expected to get back 5, and instead you got this runtime exception where it blew up and it said could not access this REST service to do my addition function, you'd be pretty surprised. You'd be like, well, why do you need this other service to just do this simple add function, right? And that's what you want to avoid. You want to avoid surprising the user of your service with these dependencies that they only find out about at runtime, where the only way they would know that that dependency exists is if they actually looked at your source code and tracked down every call that you were making that might have some third-party dependency. Things that will break your stuff at runtime are dependencies on infrastructure, primarily, right? So your service needs a database, your service needs a file, your service needs some config setting, needs to talk to a network service or send an email. All of those types of infrastructure dependencies will make it very hard for someone to use your class at runtime unless they've provided them, unless they've set them up. And so those are the things that you want to advertise so you don't have these deceptive constructors where it says, oh, I don't need anything. You can just new me up and I'll just work. But then at runtime, you're constantly chasing your tail trying to figure out, well, why does it need this? And what does it need now? And what broke this time, right? At compile time, everything seems fine. And then at runtime, you end up chasing down this rabbit hole trying to figure out what the deal is. So follow explicit dependencies principle. If your class needs any of the stuff I just mentioned, make sure you're asking for it in the constructor. Need to talk to a web service? Fine. Ask for an interface that represents that service. Same thing for config, for data access, web, sending emails, anything like that. Ask for it in your constructor. All right. The other thing that's related to this is that your abstractions, these interfaces, need to be defined somewhere that they can be accessed by your high-level classes and your low-level classes. So those low-level implementation services need to implement those interfaces. Your high-level business services are going to work with those interfaces as their dependencies. Those are the things that are going to be injected into their constructors. And of course, your user interface needs to wire all this up. So when we're thinking about where should we put interfaces in our system, which is a common question I get, this helps inform that, right? This is telling us they need to be pretty much universally accessible by the different parts of our system. And so we're going to have to put them in a project that everybody can get to. Now, on the topic of interfaces, if you're not using them all the time right now, here's something that helps really drive home the importance of them. If you don't use abstractions, if you don't use interfaces, and you just new up other classes anytime you need something, which is how probably most of us learned how to program to begin with, your code is going to look like this. On the left, at compile time, it's going to look like what you see here, where class A instantiates class B, calls a method on it. That method instantiates class C and calls a method on that. All right, now you run that program and the call stack looks identical, right? The control flow is going to be that class A then calls into class B, which calls into class C, and they're just one for one, parallel paths. Right, and so this is the easiest type of code to understand and walk through and follow. And like I said, it's how most developers learn when they're starting. When you do Hello World, you probably don't do Hello World with a bunch of abstractions and interfaces and things like that. In fact, there's a lot of jokes online about what it would look like if you did. But when you want to build enterprise software that can be easily maintained over time, and you want to be able to leverage certain design patterns like decorators and things like that, being able to have some degree of abstraction or interfaces can be very valuable. And one of the things that gives you is this modularity, where you can say, okay, at compile time, I'm going to have class A reference this interface B, and class B is going to reference this interface C. And class A has no knowledge of the implementation details of class B. And likewise, B doesn't know anything about class C, right? At runtime, it can still do the exact same thing as it did before. But now at compile time, I have that flexibility where if I need to swap out a different implementation, either in a different environment or a different version or while I'm testing, I have that flexibility. I can make that change very easily because I put those abstractions in place. All right, so one of the things that we want to do in our architecture is make it so it's easier for developers to do the right thing. Or I like to say we want to make the right thing easy and the wrong thing hard. Developers tend to be somewhat lazy. We're going to do the thing that's the easiest to do, that's going to help us get our job done the quickest. You can call it lazy, you can call it efficient. If we have a coding system where everything is done a certain way, most of us are going to tend to want to keep it consistent and follow the same conventions that are there. So we want to have an architecture where the default way of doing things leads to the right results. And we want to kind of force developers to fall into the pit of success, right? If they just do the default thing that's in this architecture, it should lead them to a good place. It should not result in a lot of pain and suffering. So to make the right thing easy and the wrong thing hard, we want to make it more difficult for UI classes to directly depend on infrastructure classes, right? We want to have that separation of concern. We want to have that loose coupling. So we don't want to have controllers that are just newing up data access classes and then mucking with the database directly in the controller. And then somewhere in there, there's probably business logic mixed in too. All right, so we want to think about this principle, this idea, when we're looking at how to structure our solution to see if we can make it so that this rule is something we can enforce. Similarly, we don't want to have our business or domain classes depending on infrastructure because that breaks the dependency inversion principle. We don't want the high-level business logic classes that are working at the abstraction of, customer adds an item to their cart to be working at the low-level details of, insert this record into this table in this database. We want that dependency to be inverted to follow that dependency inversion principle. And then we also want to keep repetition to a minimum. So I didn't mention the don't repeat yourself principle, but the dry principle is another fundamental principle of software development. We want to make sure that if possible, we're able to encapsulate cross-cutting concerns like validation logic, query logic, different policies in such a way that they are reusable within the system and don't require a lot of copy-paste coding or other techniques that over time lead to a lot of technical debt. So what can we do to make it so it's easier to apply these concerns than copy paste, which is not that easy to do, right? Because copy paste is really easy to get done. So we want something that's even easier than that in our system. All right, so let's look at what classic n-tier architecture leads us to and consider what this does in terms of the dependencies and whether it meets the needs of these principles. So take a look at this this diagram here from 2001, which I actually used in my first conference presentation back in the day. And just examine that for just a sec while I have a quick drink of water. All right, so on the left here, we have this so-called classical layer where we have no separation into different tiers or layers in our architecture, and everything is grouped together. And so if you've ever worked with classic ASP scripts from the 90s, that's what most of them look like out of the box. It was basically VB script, or you could actually use JavaScript as well, intermixed with HTML and data access and business logic, all in one file, and it would just get executed from the top to the bottom. This, it turns out, was not the most maintainable way to write software, and so this diagram came about in the early part of the century, where we realized, like, hey, we could take some of these common concerns, we could split them out, make them their own layer. So the first one, the obvious one that people would pull out would be the data access layer, and we would make some set of scripts as a library or even a COM object using VB6. And encapsulate all our data access there, and then everything else would reuse those and call them. And then, you could separate out the business layer as well, and possibly a workflow or application layer on top of that, and basically use as many of these different layers as you found useful and valuable for your team and your system. Now, the problem with this approach is that it didn't have any abstractions. And so you ended up with an issue with transitive dependencies where the data access layer depends on the database and business logic layer depends on a data access layer. So that means it depends on the database. The UI layer, the same thing. And that means everything depends on the database. So this leads to a very database-centric design. And if you want to do automated testing, which you pretty much need for rapid development these days, and if you ever want to get to the nirvana of continuous delivery, where you can do a commit, and if all the checks pass, it just goes to production, you really need automated testing. Automated testing with a database is a lot slower than automated testing without a database. Now, you still need to do some testing, like integration testing and some other types of tests, probably that include the database if you want to have confidence that in production, where that database is going to be there, that everything works, right? But you don't need to test every little bit of your business logic through a database, especially if your database logic doesn't contain all your business logic, which it probably shouldn't. And so it'd be nice if we could test the business logic layer in isolation from the database. And the same thing for the UI layer. Right, we should be able to test these things without the need for a database. And that means we need to change what is the center of the universe for our app. It shouldn't necessarily be the database if the database is just a persistent store. That's sort of a side concern, right? It's like, yes, we need to store the state between this request and the next request, but that's not the most important thing in the application. The most important thing is that our business logic runs correctly, right? And it's nice that we can get that state back when we need it, but we're not going to design our entire architecture around it. Instead, we're going to use what's called a domain-centric design. And we're going to put our domain logic, our most important part of this application, the whole reason why we're building it is to encapsulate this business logic and these domain rules. We're going to put that at the center, and we're going to make everything else depend on it. And so your domain model in a system like this is not just your business logic, but also tends to be a model of the problem space. And it includes different patterns, different types of things like entities and value objects and interfaces and services, and all those types that we model inside of this application that help us solve customer problems in a consistent way that we can easily reason about and test and verify. So interfaces are one of the ways that we define how we're going to work with those domain objects. And so we're going to use interfaces to get domain objects to and from persistence, and we're going to have various services that operate at the level of these domain objects. And then everything in the application, all of the infrastructure details, how they talk to a database, if there is one, how they send messages, how they do those types of things, and all the user interface is going to depend on these domain objects. All right, so when we talk about clean architecture, it's really just another name for other architectures that have come before it, which are onion architecture, hexagonal architecture, ports and adapters. They all have the same idea that the business logic and the abstractions that we're going to use to model the problem should be at the center of the dependencies in our application. And so if we take this diagram here, which comes from onion architecture, and you look at the center few rings here, right? At the very center, you have your domain entities. Those represent the most fundamental things in your system that tend to have some state, that tend to have some ID that we're going to use to track them and persist them over time and see when they change and be able to load them up with their changes between one request and the next in a web system. We're going to access those using repository interfaces. So that's just one of several abstractions we can use. And that's an abstraction that we give a particular name to so that when we communicate with one another, we know that this particular service is all about data access and persistence. A repository is basically just a service, but we use that name so that everybody knows when we say that word, we're talking about data access and persistence. Other services as well will operate on these domain entities, and that's what this other light blue layer has. Now then, those three layers combined make up our domain model, right? That's the center of the application. Everything else in the purple region is just the rest of stuff, right? The rest of everything else. So you've got your infrastructure that knows how to talk to a particular database or log to a file or send an email. You've got your UI, whatever that is. So, if something needs to communicate with the user, whether it's a mobile app or a web app or whatever it might be, that's external and depends inward on this domain model. All of our tests are out here as well. The main idea here is that the center of the universe is that domain model and that domain logic. Another view of this is this ports and adapters hexagonal diagram. And if you ever wonder where the hexagonal architecture name comes from, it's because somebody decided that a hexagon would be good to use on a diagram like this. If they'd used a triangle, we'd have triangular architecture, I guess. So it's kind of an odd name to have latched onto. But more interesting as a name, I think, is ports and adapters. And so if we look at this diagram, we see these purple circles here at the center. Those are ports that our domain layer exposes, and other things can be written to fit those ports, right? This is just like the plugs in your wall that you can plug your lamp into. And so each one of these ports represents an abstraction that a particular implementation can plug into. And if we look at this persistence port up here in the top right, this is how we're going to persist our domain model to something, to wherever, right? So that if we need it later, we can get it back. And we can implement that using an in-memory object store or a SQL Server or Oracle or other relational database model system if we want. Right, we can swap those out at runtime and have the system behave entirely differently from a persistence perspective. And we can expose ports for any of those different types of things that our domain model might want to plug into. So those ports are basically just interfaces, right? Those are the abstractions that our domain model exposes that other parts of the system can plug into. And in order for that to work, those other parts of the system need to depend on this domain layer in terms of a dependency chain. The other thing that's important to keep in mind is that these dependencies need to be unidirectional and they shouldn't have loops in them, right? You don't want to have your UI layer depend on your business layer, which depends on your UI layer. Those cyclic dependencies are not a good thing, and Visual Studio generally won't allow you to do that. So if you have project references going from project A to project B, you can't then go from project B back to project A. You'll get an error when you try and do that. And so we want to make sure that these dependencies flow in a single direction and that they flow toward the core of our project where that domain model lives. So the rules of clean architecture, the most important fundamental rule is that the application core contains the domain model and all of its abstractions. The corollary to this then, or the second rule, is that all the other projects depend on the core project. And if you think about this like the onion architecture, you want to have that core at the center and all the other dependencies point inward toward that core. Those inner projects have to define interfaces. That's where they need to live in order for other things to get to them. All the other projects implement those interfaces. And sometimes the domain model itself will implement interfaces defined there too. You also want to avoid direct dependency on the infrastructure project. There should be very few places in your system that use directly the types from infrastructure. The two exceptions to these are going to typically be your integration tests that need to make sure those things actually work. And then the startup file in your web application, if you're using ASP.NET Core, will typically have knowledge about the infrastructure project because that's where you're going to wire up those dependencies. You're going to wire up the abstraction, the interface, to a particular implementation that lives in the infrastructure project. Okay, some of the features of clean architecture are that it is framework independent. We can use this with ASP.NET or ASP.NET Core or Java or whatever else. It doesn't really matter. It works well with any of these systems, especially strongly typed systems like .NET and Java, for the reasons that we've laid out here. It's database independent. It doesn't care what database you're using. If you're using a database, database information is just not an important concern. It's kept at arm's length from your system. Same thing with UI, right? It doesn't really care about the UI. So you can use it with just about any type of structure that you're trying to build that would benefit from these principles that we've laid out here. It's also very testable, which again is very important if you're trying to build software that you can ship rapidly. Testing is important to ensure quality. Manual testing is very slow and expensive and error prone. Automated testing, computers are really good at, and computing is getting cheaper and cheaper, whereas developer salaries are going up and up. So it's better to take our tests and move them into something that the software can do for us than to try and rely on manual testing. And so having a very testable architecture that can have tests run rapidly and consistently without failing for random reasons because something changed in the database is very important as well. So if you have an existing system and you've listened to what I've had to say so far and you've said, okay, Steve, I think clean architecture sounds great. How do I get there? All right, well, you can try refactoring your existing system to a clean architecture system. And the easiest way to do this is if you're doing a port from, say, .NET to .NET Core, and you're going to start with a new solution. And if you do that, then you can start with a properly organized solution like my clean architecture template that I have on GitHub. And I'll talk about that more in just a few minutes. And so if you're able to do that, which is it's almost a full rewrite, at least it's a port, right? You're going to copy and paste a bunch of C# code from one solution to another. This works really well because you've already got everything laid out the way it needs to be. Your dependencies are all set up. The tests are all in place. And it's just a matter of dropping things into the right locations. The solution structure will kind of keep you in that pit of success and keep you from going down the wrong path. The next best is if you already have an application that only has one project. So you've got just an ASP.NET or ASP.NET Core web application, and everything is in there in different folders. And you want to be able to move that to a multi-project structure so that you can enforce some of these rules as far as the way dependencies should flow. That tends to be the next easiest way to get there. The most difficult is if you have a large n-tier structured system where all the dependencies are flowing the wrong way. From a clean architecture perspective, right? Where you've got that transitive dependency, where you've got a UI layer that directly depends on a business layer, directly depends on a data layer that's tied to the database. Refactoring that will be the most expensive and difficult. And that may be a case where you want to, if your team is not already super familiar with clean architecture, you may want to bring in a consultant or someone that's done it before to give you some help. All right, so now let's talk about the different parts of an application and specifically what goes into each project, and then we'll jump into some code. So if you're looking at your core project, which is where your domain model is going to live, in Visual Studio, in this project, you're going to have your interfaces, which I've mentioned. You're going to have your domain model types like entities, value objects, aggregates, which are a domain-driven design pattern that you're probably familiar with if you use DDD. You may also have domain services. These are going to be just classes that just have behavior but no state and do operations on your domain model. They don't have a direct dependency on a particular type of infrastructure, so they can live inside of your core project. You may have domain-specific exceptions. I'm a big fan of custom exceptions for domain model types of things that might go wrong. It's much easier to diagnose something where you get an exception that says, order did not exist, than something that just says null reference exception. And you've got to go track down, well, what was null and why was it null and where did that come from? So anywhere that you can use an exception in the language of your domain to represent something that was just wrong and a state you should never get into, create an exception for that. It takes almost no time, right? It's like 2 lines of code and you've got an exception that'll save you trouble later when you're trying to figure out why something's not working. The other things that you might use in your domain model are domain events and domain event handlers. Domain events are another DDD pattern that I'm a big fan of. They do a great job of decoupling your system and helping it follow open-closed principle and other solid principles. So those would also live in this core project typically. You might have domain event handlers in other layers of your project. I show an example of that in my DDD fundamentals course on Pluralsight, where we use a handler inside of the web project to do communication over SignalR and pop up notifications to the user. But a lot of the times, if your handlers are doing business operations and business logic, then those handlers would live inside the core project with the rest of the domain model. Another pattern you might use that can really help your application stay clean is the specification pattern. And I could do a whole talk just on the specification pattern, and there are Pluralsight courses that talk about it as well. I'll show an example of it here, and I have a NuGet package called Ardalis.specification that you can use to give you a jump start on this. But the really quick version of it is you can take your query logic and encapsulate it in a class. That class is a specification. Now, instead of having query logic just all over the place inside your repository or scattered all over your application inside your controllers and services, you can embed it inside these classes. You can give these classes special names, like custom names that say what it is they're specifying. And then anywhere you need that type of query, you can use that same specification. So they give you code reuse, separation of concerns, and a host of other benefits. And we'll look at those in a minute if we have time in the code. All right, so that's it. That's pretty much what goes inside your core project in a clean architecture style ASP.NET Core application. So then the next project that every solution will probably have is the infrastructure project. And infrastructure is where we put things that talk to out of process resources, right? Anything that's not in memory inside the thread of your C# application where you need to communicate outside of that app should have an infrastructure implementation. So this is going to be things like data access. So your repositories, if you're using that, would be here. Your DB context for Entity Framework or EF Core would be here. If you're going to have cached repositories, which is a great pattern to use for performance reasons, those implementations would also be here. Any web API clients that you have, because you're communicating with other web APIs, right? You're talking to GitHub's API, you're talking to Twitter's API, you're talking to some other microservice inside your own organization over HTTP or even gRPC, right? All those clients would be inside of infrastructure because they're talking out of process. Anything that talks to the file system, anything that's doing logging, those adapters would live inside of infrastructure as well. Anything talking over the network, email, SMS messages, things like that. Talking to the system clock. If you need to do behavior based on what time it is or what the date is, that should be an abstraction that you use, and then you can implement that with a system clock adapter in infrastructure, and then in the rest of your code, you can just use that interface. Then in your tests, if you want to say, hey, what happens in this test when it runs at 4 o'clock versus when it's midnight, right? You can easily swap that out because you've got that seam, you've got that adapter, and you don't have to have a test that only runs or only passes at certain times of day. Other services would also live here, and potentially interfaces. So there might be interfaces that live in the infrastructure project. That should be the exception, not the rule. And why would you put an interface in here instead of in core? Well, generally this is if you have interfaces that work at the level of the infrastructure types that they're dealing with. So if you have a third-party SDK, right, you're working with AWS, you're working with Azure, and you have this SDK and it has types that you want to use in an interface, like I need an Azure Blob Storage thing back from this method I'm going to call. All right, well, Azure Blob Storage type is very tightly coupled to a particular implementation. So we don't want to have the Azure SDK as a reference from core, which we would need to have if we had an interface that said that this method returned an Azure Blob Storage type. And so that interface will have to live in infrastructure and not in core or application core for our system. Things that don't have dependencies on specific implementations those interfaces should generally live in core. All right, so now the UI part of your project, if we're talking ASP.NET Core, is going to be this web project. And the things that go in here are going to be all the UI concerns, mostly ASP.NET components, right? So if you're using controllers and views or you're using Razor pages, all those things are going to live in that web project. If you're using any models for DTOs, for communicating over the wire or binding to your views, those are all going to live here as well. Any type of MVC related pieces that you're doing that are custom, whether that's custom filters or custom model binders or tag helpers, would all live in the web project too. Now, if you want to reuse these things and put them in a separate project, that's fine, but then the only thing in our application that should depend on those reusable libraries would be the web project, right? We don't want to have a dependency from our core project onto some reusable library full of custom filters that you've written that's only specific to MVC. You might have other services in your web project as well. These would follow kind of the same rules as for infrastructure. We only want to have these services and their respective interfaces in this project if they are operating at the level of web-related concerns. So if you have a service that returns back a view model, and that view model is defined in the web project, then the interface for that service, if you have one, would need to live in the web project as well, because that's how that works, right? That's the only place it's going to be able to reference that view model that interface is using. All right. So those are the three main pieces of clean architecture. You got the core, you got the infrastructure, and you've got your UI, which for ASP.NET is going to be web. If you have multiple different applications and you have logic you want to share between them, there is one third or fourth, I guess, project that you might use, and that's called shared kernel. So shared kernel is another domain-driven design concept. That's where the term comes from. And it's basically used for things that are going to be consumed by a bunch of different bounded contexts or a bunch of different applications. And so these common types typically get referenced by core and anything else in the solution. And so these should be distributed ideally as NuGet packages. And the reason for this is because it gives you a lot of flexibility when you go to deploy, because you could have 3 different solutions that are all using your shared kernel version 1.2. One of them needs to now make a breaking change and upgrade to 2.0, but the other 2 are about to ship. Right. Well, those 2 can still ship and still run on version 1.2, and the developers working on the third one can take in that breaking change, use version 2.0, and they can ship as well, and they can all be working side by side because they have different version NuGet packages. If you are following a code sharing approach where this is all just shared code in a library that gets compiled into all the solutions at the same time, that's much more difficult to do. Things that might go in shared kernel would be base types that are used in your domain models. So base entities, base domain events, base specifications, common exceptions, interfaces, common auth and user types, or common DI, dependency injection, things that you might be using if you're going to use autofac, for example, everywhere, and you want to wire up certain things about how autofac works, you could put that in shared kernel, and now you would have access to autofac everywhere. Common logging stuff, same idea. Common guard clauses could go here. Quick segue, let me just tell you about guard clauses. A guard clause is just a pattern that you can use to get rid of code that looks like this. where you're checking for null, and if the parameter is good, we go into the if statement, and if the next parameter is good, we go into that if statement. And so the part that's actually doing the work is right here, where it says process order here. But all the rest of this lines of code is all just error handling code for invalid inputs. A simple guard clause is I'm going to check for the bad cases first, and I'll throw if I have a problem. And what that means is that I don't need to have nested if statements. When I get down to this level here, I know I've processed all of the arguments and I know they're good, so I can just do my happy path at that point. Now, even this results in a fair bit of duplication. So if you want to standardize on certain things that you're always checking, and it's not just null, right? Null is one of the more common ones, but nullable reference types are something that you'll probably be adopting if you haven't already, and that gets rid of a lot of these issues. But you might have other types of checks you're doing on these inputs all over the place inside your domain. So you can use this common guard clause package, which just recently exceeded 1 million downloads, so people are apparently using it. You can use this package to do these common checks in a consistent way, and you can define your own extensions for it. So if your business has a particular thing you're always having to check, you just create a guard clause for it and you check it, and then you can proceed to do the rest of that method. All right, so then our solution structure ends up looking like this. We have web depending on core, infrastructure depending on core. Core depends on shared kernel, which should be a NuGet package. Notice that web and infrastructure don't have a relationship here. All right, at runtime, web needs to know about infrastructure. So somehow the DLLs from infrastructure need to be accessible to web, and that could just be a matter of copying the files from the bins folder of infrastructure into the bin folder of web, and then loading them up with reflection. And if you do that, then you will have no actual project reference from web to infrastructure. It will be impossible, short of reflection, for your developers to accidentally consume or new up or use infrastructure types inside the web project, which could be really good. In practice, most of the time, we do just add a project reference to infrastructure because it's more convenient and it's easier, right? But I just want to point out, you don't have to have a reference there at all. You could have them be completely isolated from one another at compile time. Then you're going to have tests. You're going to have unit tests for core. You might have unit tests for other things as well, but core is especially unit testable. You're going to have functional tests for web. Functional tests are a special type of integration test that actually leverages the whole MVC stack. So these test everything from routing to model validation and filters, and not just does the action method run, right, which is all a unit test would be able to verify. And then you'll have integration tests at different levels as well, but most of them will probably be targeting infrastructure. So your solution structure looks something like this. You'll have your core, infrastructure, and web as your primary source code folders. I tend to use solution folders for separating my real code from my test code. So then in your tests solution folder, you'll have your various tests for your different projects. I'm going to skip by, in the interest of time, a discussion about how to organize your actions and handlers. So I'll just zip by this. Shows different ways to organize them. And then let's talk about these 3 projects that we will look at real quick. First one is eShop on web. This is a Microsoft reference app that you can use. Actually has a real running storefront application as a sample. It's a monolithic app. It doesn't use microservices. So 95% of the apps you're going to build don't really need to be built with a host of microservices. They work just fine as a monolithic application, still broken up into different projects like we've shown here. And that's what this uses. If you want to have a starting point as a template for you to start, this clean architecture thing is not a sample app per se. It's just a solution template. So you can take this, unzip it, kind of replace some of the things that are in there, and then have a working template for your application. In fact, if you don't want to have to waste your time renaming the namespaces and things, you can install a template. There's a Visual Studio one that you can get from that page, or you can install it right here with .NET New, and then you can just say .NET New clean arc and then -o, acme.myproject, and it will create the thing with the proper namespace for all the pieces. We'll also take a look real quick at API endpoints, which are a way to organize your APIs so that you just have one endpoint class per actual REST endpoint that you have, or API endpoint that you have, which makes it so your controllers are not these massive things that get out of control, but instead you just have a single endpoint to look at for each one. So we've got about 5 minutes left. Let me jump into some code with this. So eShop on web looks like this. It's got application core at its center. Its entities include things like a basket and a buyer and an order. You can use this to kind of get an idea of how basic domain-driven design patterns work. There's custom exceptions, like I mentioned. You have things like basket not found, and it has a bunch of specifications that are used. So instead of having a repository that has a bunch of different custom methods that have different ways to fetch data, and especially with Entity Framework, you often have to have different methods to say, I want to get the order. I want to get the order with the order items. I want to get the order with the order items and the associated products. Right. Well, you can do that with a specification here, and the specification is really tiny, right? It just says, give me this query where, this buyer ID, and then include this and include that. All right, and you can easily test this specification, verify it's correct using a unit test, because this doesn't have any dependency on Entity Framework or a database. I can just run this against an array or a list and verify that I get back the right results. But then at runtime, when I do run this with Entity Framework, it's going to use this query to create the proper SQL to do all the filtering and include stuff on the database. So I'm not having to do that in memory. And again, to do all that, this is using the Ardalis specification package here to take advantage of that. So that's another NuGet package you can use. If you look at the clean architecture template, it looks very similar. So this is clean architecture. It has a web project. It has starting pieces, very minimal starting pieces for each of the different type of ASP.NET Core app you might build. So if you're doing a controllers and views app, it has a basic controller and views to kind of get you started with that. If you're using Razor Pages, it has basic Razor Pages in here as well. And if you're doing an API with controllers, it's got a base API controller you can start from in an example. If you're doing endpoints, it has an endpoints version of that as well. If you do API endpoints, the difference is something like this, right? Here's my to-do items controller. It takes in some dependency, and then it has a bunch of action methods that do, CRUD operations. If I want to take that exact same logic and break it up into individual API endpoints, it would look something like this. So I would have an update endpoint, and you can see the entire class fits on one screen. And this is a generic endpoint that tells me what the request and response are. And those requests and response are right here. So I don't have to go, spelunking around in my code trying to find the API models folder somewhere to figure out what this DTO looks like. All the DTOs that you use with these endpoints are right off of them, similar to how you get that same behavior with API endpoints, or sorry, with Razor Pages, where the Razor Page has its model chained right off of it. All right, so that's API endpoints are basically the same organizational principle as Razor Pages, but for APIs. If you want to look at API endpoints, they're another NuGet package you can get. Here's what the sample looks like. It is a trivial amount of code inside of this. So there's basically just these two classes, a base endpoint and a base async endpoint, and each one of them is like almost no code, right? So these endpoints are just controllers. Right, they just inherit from controllers. So there's no magic here. I didn't reinvent MVC to make API endpoints work. All they do is provide you with a pattern where you're expected to just have a single handler per endpoint instead of having a host of different action methods on a controller that violates single responsibility and gets out of control. And so again, you get this nice behavior here where you can just have your DTOs directly associated with the endpoint they go with. I think that's about all I've got time for. So let me jump back here, show you some resources, and happy to answer any questions that we've got lined up.
Thank you so much, Steve. I'm looking at the questions tab here in Teams, and there is a like-minded person who says, great talk. So congrats, first of all.
All right, great.
Then we've got a few questions here. I'm going to start with the second one, and you're going to figure out why later on.
All right.
The second question is the shared kernel a single project, or is it also having several shared kernels or shared kernel projects? A core shared kernel project and a shared kernel infrastructure project?
Usually it's just one. You could have several, but you don't want to have infrastructure in shared kernel because all of your core projects and all of your applications are going to depend on it. So the rule that your core project shouldn't depend on infrastructure is extra true for your shared kernel because all of your core projects in all of your solutions are going to depend on it. So if it depends on a database, now everything depends on a database. So it should be abstract. If you do depend on a particular implementation, like I gave the example of AutoFac, you should have it be an implementation that does not bring along infrastructure dependencies. So something like AutoFac is just code, right? And it just runs in process in your system. So that's one that's generally pretty safe to depend on. But Entity Framework is not, right? Entity Framework has a dependency on a database. You wouldn't want to depend on Entity Framework in your shared kernel or in core.
Pretty clear, I would say. Questions keep coming. The next one is related to the support for Blazor. Where is the Blazor project over here? Or what would you recommend?
For Blazor, the eShop on Web sample that I talked about actually has Blazor support now. We added that this past summer. So there are 6 projects in here. It used to just be 3, but to support Blazor, there's a Blazor admin section that manages all the items in the catalog of the store that you can use as a sample. It's using Blazor WebAssembly. There's a Blazor shared project that shares data with that client-side code. And then we created a public API for the Blazor app to talk to, because the base web application was not set up for that. So we created another project just to be the API for the Blazor. So if you're looking for a Blazor sample that follows clean architecture, I would look at the eShop on Web for that.
Super. And the last question, which I suppose would open quite a conversation, but let's just tackle the first, I don't know, the beginning of the conversation. Let's just open the conversation. The question is, how clean architecture differs from hexagonal and onion architectures?
It doesn't substantially. I'm sure there's probably some different terminology differences, like whether something's called a port versus an abstraction or things like that. And different architects will implement them with different design patterns that they might like or not. But the basic idea that the abstractions and the business logic lives at the level that everything else depends on, as opposed to everything depending on an implementation that then itself depends on a database or an external infrastructure, that's the key difference. That's the application of the dependency inversion principle is the key thing that all of those architecture styles have in common.
Okay, so I lied. That was not the last question. I'll let them ask the last one.
All right. Another question just popped up. How will Swagger work with API endpoints?
It works just fine. Let me see if I can run this real quick and just show it. But you might have noticed when I had the code up for this one that I had some Swagger details here. And you can specify all that. You can do that in a controller as well, but I'm doing it here in the endpoint so that I could show them here, right? So all the details of, this post creates a new author and has all the stuff here. This runs just fine off of API endpoints. So again, it's just ASP.NET Core controllers under the covers. Everything that works with ASP.NET Core controllers still works with API endpoints.
Super. So Steve, you're doing a lot of consultancy and training. How does clean architecture look in the trenches?
How about what is it?
How does clean architecture looks like in the trenches? Because you're doing a lot of consultancy, you're seeing a lot of teams, companies, and so on.
That's where my GitHub open source stuff all comes from, right? Like doing it for real clients is where I get the ideas for what works, and then that's what I put into the open source project. So, API endpoints is being used by real companies. Clean architecture, that template's being used by real companies. So that's how I pay the bills, and I take that information and I put it into these open source projects so that I can have my clients use them and have other clients benefit from them as well.
Yeah, that's really useful. But I think let me rephrase the question. Do you see enough adoption of the clean architecture?
Definitely, it's increased with .NET Core, right? So .NET Core makes it a lot easier to follow this approach, and in fact, it makes it so it's kind of the default approach that you would expect to follow. Because it's using dependency injection and dependency inversion everywhere, and it's sort of how .NET Core is architected itself. For full framework.NET, most things were generally using the N-tier structure where you had UI depends on business layer, depends on data layer. You did have some folks that were inverting it, but it was definitely the minority. With .NET Core, I think it's the majority are following something that's more domain-centric in design. And as more and more folks adopt microservices lend themselves very well toward domain-driven design and concepts like bounded contexts, and all that stuff works really well with the clean architecture approach. They all complement each other very nicely.
Thank you. I very much enjoyed your presentation and the entire conversation that we had.
Yeah,
Thanks.
thank you, Steve. It's been a real pleasure and very insightful. And yeah, what can we say? Hope you have a great holiday and Christmas and New Year coming up, and hope to see each other next year as well.
Likewise. Yep. Happy holidays. Merry Christmas. Happy New Year. Enjoy the rest of the conference, everybody. Thank you.